Hello friends, Mr. Burrell here. We're at the end of Unit 11, and really the end in this trimester in Math 2, talking about quadratics. We've talked about factoring quadratics. We've talked about solving quadratics. Now we just are finishing the lessons, the unit covering graphing quadratics, dealing with quadratic graphs. So we're going to review all the things we discussed in this unit pertaining to quadratic graphs, some of the characteristics of quadratic graphs, some of the different forms that quadratic functions are given in that will help us to graph quadratic functions, etc., etc. Okay, so first, something to remember, every quadratic equation has two solutions. And we've been talking about this since the beginning of Unit 10 when we were talking about solving quadratics. You can either have one real solution repeated twice, two real solutions, or two complex solutions. And when I graph those, this is what they might look like. If I touch the x-axis here, if I touch the x-axis in one place, that one spot on the x-axis where I touch represents the one real solution to this quadratic function, or another word for solution that we've talked about is zeros. So where y is 0, where I cross the x-intercept, I have one real solution. I have the situation where I have two real solutions, meaning I cross the x-axis twice. So there are two zeros, or there are two solutions. And that's what the graph would look like. I also have found the situation where I have two complex solutions, or imaginary solutions, which mean it doesn't cross the x-axis at all. So those two solutions that quadratic has are not real solutions, meaning they're not a real number, but they will be an imaginary number. So when I don't cross the x-axis like that. So that's something that we reviewed in association with graphs at the beginning of this unit. So, in the very first unit, in the very first lesson, we started by talking about different forms that quadratic functions can be written in. We have standard form, which looks something like this, ax squared plus bx plus c. That's the form that we often see quadratic functions written in because it's the most simplified form. We also talked about vertex form. So when I have something like this, x minus h squared plus k. The convenient thing about a quadratic equation in this form is I can really easily identify where the vertex of that parabola is, or the vertex of that quadratic function. In this case, the vertex would be at 4, 7. It's really easy to determine that from this form. The other form that we talked about is factored form. So when I have something like this, x minus r and x minus z, or x plus r and x plus z, two different factors being multiplied together. The reason we like this form is that in this form we can really easily identify where the zeros are, or where the quadratic function or the parabola crosses the x-axis. When I set both of these terms equal to 0, when I set y equal to 0 here, and I set these terms equal to 0 like I did in Unit 10 when I used the zero product property to solve quadratic functions, I can find where that quadratic function crosses the x-axis. So these are the different forms, and these are, in each of these forms there's some specific characteristics, some specific things that we can really easily identify about quadratic graphs. Okay, so we started by just kind of identifying some basic characteristics of these graphs. So for example, this graph is given to you right here. Before I even look at all of this jazz, I'm just going to look at this. Well, I know that this is the vertex. I'm going to cross the y-axis here. I'm going to cross the x-axis right here and here. I can draw an invisible dotted line right through the vertex to get my axis of symmetry. Okay, so some of the basic characteristics of quadratics that we discussed. The vertex is the point where it goes from increasing to decreasing, or if it was like this, it would be the point where it goes from decreasing to increasing. So let me draw that again, sorry. So the vertex of this function is 1, positive 4. 1 in the x direction, 4 in the y direction. Then is that vertex a maximum or a minimum? Is it a mountain or is it a valley? Well, it's a mountain. It's up top here. It's facing downward, so that's going to be a maximum. That's the highest point. Because that's a maximum, the concavity means which way is it pointing? Which way are these arrows pointing as it keeps going? Well, it's pointing down, so that's going to be concave down. And the axis of symmetry is right here, the x value, where I could perfectly fold the parabola in half. So I'm going to call that x equals 1. Because at x equals 1, that's where the axis of symmetry is. It passes right through the x-coordinate of the vertex. The zeros, or the x-intercepts, are at x equals -1 and 3. -1 and 3 is where I cross the x-axis. And the y-intercept is at 3, because I crossed the y-axis at +3 here. So given a graph, I can identify all these different characteristics of that quadratic function. Lots of these we already learned how to identify at the very beginning of this trimester when we were talking about some basics about graphing. Now we kind of added some more things that we can specifically identify in a quadratic graph. Okay, here, and this is a question from your review, homework problem number 6 on your review. This says y equals 2x minus 5 squared minus 5. So this is in vertex form. So right off the bat, I know that this is a quadratic function that has been transformed. So this number in front, 2, that won't affect if it's upside down or anything like that. It'll just affect how skinny it is. And then this right here means I'm moving to the right 5 spots and down 1, 2, 3, 4, 5 spots. So I move the opposite direction so I move left to right according to the number that's inside the parentheses, opposite of the sign that's given. I move up and down according to the number outside the parentheses, the same as the sign that's given. That's why I'm going right 5, down 5. So my function is going to look something like that. Not perfect yet, but it's going to look something like that. So my vertex is at 5, -5. And 5, -5, this point right here is a minimum because it's a valley there. It's at the very bottom. Concavity, these arrows are pointing up. So this is concave up. And the axis of symmetry is right here through the x-coordinate of the vertex. So at x equals 5. So those are the basic characteristics that we discussed in the first lesson in this unit. Some of these basic characteristics of quadratic graphs. Next, in 11.2, we talked about converting from standard form to vertex form. If you heard that on the intercom, apparently they need a custodian in the office. Anyways, we can change any standard form quadratic equation into vertex form in order for it to be easier for us to graph it, to find where the vertex is. So here, and these are homework problems on your review as well. This is homework number 10. This is homework number 12. So in order to find the vertex, in order to find the x-coordinate of the vertex, or the axis of symmetry, I find the axis of symmetry by taking -b divided by 2a. That's a formula for the axis of symmetry, that vertical line that could fold the parabola in half. Well, in this case, we have negative, this is a, b, c, b is -4, and then 2 times a is just 1, because there's nothing in front of the x squared. So that ends up being a +4 divided by 2, which is 2. So my axis of symmetry is going to be at x equals 2, just right there. So now in order to find what the y-coordinate of the vertex would be, I need to plug 2 in for each of these x's. So I'm going to rewrite this equation instead of, except wherever I have an x, I'm going to replace with 2. So this is 2 squared minus 4 times 2 plus 1. So 2 squared is 4. -4 times 2 is -8 plus 1. 4 minus 8 is -4 plus 1 is -3. So my vertex is at 2, -3. Okay, so now this question asks, change the equation into vertex form. So I'm going to go ahead and write this in vertex form, which means it's going to look something like this. Right there. So my vertex HK is 2, -3. So in my formula here, I'm going to have a times x minus 2 squared plus a -3. So then if I take care of the plus negatives and things like that, I get y equals a times x minus 2 squared minus 3. And the a value here is going to be the same a value that I started with, which in this case was just 1, so I don't really need to write it there. So the standard, or the vertex form of that quadratic function is x minus 2 squared minus 3. So it's going to look something like this. Wow, that was a pretty darn good parabola. With the vertex being at positive 2, negative 3. Again, I found the vertex using my formula for the axis of symmetry and plugging in the x value back into this equation to find the y value of my vertex, and then put that vertex back into this equation so I had an equation in vertex form. Write that form down, write that equation down, you can use it. Let's look at homework problem number 12. So this is y equals negative 2x squared plus 4x. This is a special, unique case because my c value here is just 0, but that's okay. So I'm going to go ahead and I'm going to start by finding my axis of symmetry, which is negative b divided by 2a. So negative 4 divided by 2 times a, which is negative 2. So that's negative 4 divided by negative 4, which is 1. So my axis of symmetry here is at 1. So now in order to find out what the y-coordinate of my vertex is, I'm going to plug 1 in for all of the x's in my original equation. So negative 2 times 1 squared plus 4 times 1. Well, 1 squared is 1 times negative 2 is negative 2 plus 4 times 1 is 4. So negative 2 plus 4 is 2. So my vertex is at positive 1, positive 2. There's my vertex. Okay. Now I want to put this, with my vertex being 1, 2, I want to put that into a quadratic equation that's in vertex form. So there's vertex form, where this is h and this is k, my x and my y coordinates. So I have y equals a times x minus 1, that's my h, squared, plus k, which is 2. And then my a value is the same a value I started with, which is negative 2. So there's my function. Here's my vertex. Since this value out here is negative, that means it's going to be flipped upside down. So it's going to look something like that. And as of right now, when this is in vertex form, all we can really identify really easily is the vertex. I'm not yet talking about how I can find the x-intercepts or y-intercepts. That's what I do in the next unit. So that's converting from standard form to vertex form. It helps me to find the vertex of a graph. Well, what if I don't only want the vertex? What if I want the x-intercepts and the y-intercepts? Because that's a little bit more precise as to what my graph is going to look like. Well, if I want to find that, it's going to be handy to eventually convert my equation that's in standard form to factored form. So first here, I'm going to go ahead and start. Here it asks me to find the vertex. I know how to find the vertex. So in this equation, I'm going to go ahead and find the axis of symmetry by taking negative b over 2a. So negative 8, because 8 is my b value, divided by 2a. 2 times a is 2, so that's negative 8 divided by 4, which is negative 2. So my axis of symmetry, is going to be at negative 2 here. Okay, now in order to find out what the y-coordinate of the vertex is, I need to go through and plug in for x, negative 2. Because when x is negative 2, the y-coordinate that I get will be my y-coordinate of the vertex. I'm going to go ahead and plug in negative 2 here, negative 2 here. So negative 2 squared is positive 4, so I have 2 times a positive 4. 8 times negative 2 is negative 16 plus 6. That's going to be 8 minus 16 plus 6. 8 minus 16 is negative 8 plus 6 is negative 2. So my vertex is at negative 2, negative 2. Right here is my vertex. Okay. I've already been able to do that. I've already done that. I've already found the vertex. Now I want to go the extra step and be able to find the x and y intercepts. So to find the y intercepts, I'm going to erase this stuff for a second. If you need that work, you can rewind this video. This is homework problem number 15 again. In order to find the y-intercepts, notice that wherever I cross this y-axis is where x is equal to 0. Here's x equals 1, 2, 3, 4, x equals negative 1, 2, 3, 4. When x equals 0, that's where the y-axis is. So if I plug in 0 for all my x values here, that's going to give me my y-intercept. Well, this is 0 plus 6. So my y-intercept is y equals 6, which is 1, 2, 3, 4, 5 right here. Golden. Awesome. Okay, now to find the x-intercepts. Well, notice that anywhere I touch the x-axis right here is where y is equal to 0. Here's y equals 1, 2, 3, negative 1, 2, 3. When y equals 0, that's where the x-axis is right here. So I'm going to go ahead and set y equal to 0. So 0 equals 2x squared plus 8x plus 6. Man, if only there was a way to solve this type of function. Wait, there is! Remember, we can solve this function by factoring. I'm going to factor this quadratic since it's set equal to 0 and find my two possible solutions. Okay, well, to factor this quadratic expression, first I need to take out a greatest common factor. 2, well, if I divide all those terms by 2, I'll be left with x squared plus 4x plus 3. Okay, so now I have a, b, and c. I'm going to multiply a and c together. That's going to give me 3. And I need to find two numbers that multiply to make 3 and add up to 4. Well, that's going to be 3 and 1. 3 times 1 is 3. 3 plus 1 is 4. So if I factor this out, I'm going to have x plus 3, x plus 1. Because when I divide each of these numbers by a, I'm really just dividing by 1, which doesn't change those numbers at all. So I have 0 equals 2, because that was my greatest common factor, times x plus 3 times x plus 1. Well, the zero product property says that since I have these two terms being multiplied by each other, and the answer is 0, at least one of those terms, x plus 3, would have to equal 0, or x plus 1 would have to equal 0. So when I solve for x in each of those cases, I get x equals negative 3, and x equals negative 1. So let's see, negative 3, negative 1. It's going to look something like that. That graph is a lot more precise. I can tell a lot more about that graph, where it crosses the x-axis, what the solutions are, where it crosses the y-axis, the axis of symmetry. Lots of things that I was able to do there, from being able to find the axis of symmetry and being able to put that equation into factored form. So that was 11.3, identifying the vertex, y-intercept, and x-intercepts by putting the quadratic in factored form. Okay, the very last lesson that we just finished talking about, the last video we discussed, was changing to standard form. So we're coming full circle. We've converted from standard form into factored form and into vertex form, and now we're coming back. If we have a quadratic that's in factored or vertex form, we can convert it back into standard form. And this is how we're going to do that. We're just going to simplify. We're going to follow our order of operations rules, and we're going to simplify. So here I have 2 times x plus 9 squared minus 10. Well, my order of operations says that I have to take care of this exponent first. So x plus 9 squared is the same as x plus 9 times x plus 9. I'm going to go ahead and use the rainbow method here. You can either use the rainbow method or you can use the box method in order to multiply these together. So x plus 9 times x plus 9 is x squared plus 9x plus 9x plus 81. X squared, 9x, 9x, 81. Which simplifies when I combine these like terms to x squared plus 18x plus 81. Okay, so this right here turns into this right here. So I have 2 times that minus 10. Okay, next I need to take care of multiplication. So I'm going to go ahead and multiply 2 into every term in these parentheses and get 2x squared plus 36x plus, what's 81 times 2? 162 minus 10. Now, is there anything else I can combine together? Yes, I can combine together 162 minus 10. So my final answer here is y equals 2x squared plus 36x plus 152. That's the quadratic in standard form. So now from here I could convert it back to vertex form. I could potentially convert it into factored form. This is the form that a lot of time we see quadratics in, so it's nice to be able to convert any quadratic into that form as a good starting base. Okay, what if I have a quadratic that looks like this, that's in factored form? Well, again, first I'm going to start by multiplying. I'm going to go ahead and multiply these two terms, these two factors together. This time I'll go ahead and use the box method for those who like the box method. I have x minus 10 times x plus 6. So x times x is x squared. X times negative 10 is negative 10x. X times 6 is positive 6x. 6 times negative 10 is negative 60. And I can combine these two like terms together. So I have x squared. Negative 10x plus 6x is negative 4x. And then minus 60. Y equals, and then I had this negative here on the outside. Y equals negative times x squared minus 4x minus 60. So I'm going to distribute this negative into every term inside these parentheses. So I'm going to be left with negative x squared. Negative times a negative 4x is a positive 4x. Negative times negative 60 is a positive 60. So my final standard form of that quadratic equation is negative x squared plus 4x plus 60. And again, from there, I could potentially convert it into vertex form. I could convert it back into factored form, etc., etc., etc. And that's everything. That's Unit 11. That's everything we've talked about in relation to graphing quadratic functions. Again, lots of the homework problems from the review I've done in this video. I hope that was helpful. I hope that you enjoyed that as much as I did.